Alright, I'm going to start off as I usually do with these test equipment videos with Chuck Penson's excellent book, Heathkit Test Equipment Products. Flipping to the chapter on digital frequency counters and multimeters. The subject of this video is the IB-101, a 15 megahertz frequency counter. Introduced in 1970 and carried through 1972. After which it was replaced by the IB-101, which looks just like it, but goes up to a higher frequency. So, this was delivered just in time for Christmas in 1970. It was Heath's first consumer-level digital product, and was the vanguard of a digital revolution at the company. There's a bit of a mistake here because it says it uses TTL logic on the circuit board, but it's all RTL logic. So Heathkit fairly quickly, 1 year later, introduced the IB-102, which I will also be doing a video on. I'm preparing the equipment to make it fully functional. And that was designed to go with the IB-101 kind of as an apology for its low frequency range. 15 megahertz is not very fast. So this is a 175 megahertz frequency scaler. So you connected your signal into the input of this, and then the output came out and went into the IB-101. And you could divide by 1, in other words, make no change, divide by 10, or divide by 100, and thereby get frequencies up to 175 megahertz within the span of the frequencies on the IB-101. And indeed, I purchased my IB-101 from an eBay seller who was selling it along with his IB-102, which is why I have both of them. As I mentioned, in 1972, Heathkit improved the product with the IB-101, same case and everything, but goes up to 100 megahertz. At the same time, they also introduced the 1100, IB-1100, which I also have and am restoring. And that's only a 30 megahertz frequency counter, but it's in a different case. It's much cheaper. It's more for the hobbyist, the lower end hobbyist. So it leaves off a lot of bells and whistles, build quality, simpler case, things like that. And then, of course, Heathkit fairly quickly, also in 1972, introduced the IB-1102, which goes up to 120 megahertz, but more importantly, it goes from 5 digits of resolution up to 8 digits of resolution. And I've already done a video on this one. And then finally, they went to the IB-1103 1 year later, which goes to 180 megahertz and also has 8 digits of resolution, but a different user interface. And of course, Heathkit later on went to various LED-based frequency counters, which I won't dwell on. And they even had a handheld frequency counter, which I have a video on, the IM-2400. They had the IM-2410, the 2420, those are all LEDs, 4100, and then the 4110, 4120, 4130 series, and that was their output. They never did do one that was LCD based. So here on the IB-101, I've got these 4 electrolytic capacitors that I'm going to replace. This is obviously an original. This one is newer. I'm not sure how new. This one may be newer. Some Jack Con. I don't know if that's a good brand or not. And then this other one here, wrong form factor. I'm just going to yank them all. And I've got these Cornell Dulier capacitors that will go in there, and they're the right physical size. And there those are. I think the area I'm going to find the problem with this based on my initial test, is this weird device right here. Sort of a early hybrid circuit, probably unobtainium, and the signal's currently not getting past it. So, and it's also really hard to get at down there. What fun. Alright, I've got the front panel pulled away so I can get at this area of the circuit board. Only one thing had to be unsoldered, and that was the center lead of the BNC connector. So I've got my new IC or transistor here. I've verified the pinouts with the data sheet, and I've cleaned up the solder connections. All but one are on the back side and one's on the component side, but I've verified the plate through is still intact. And I found a couple of mistakes in the documentation about resistor identifications between the circuit board, the schematic, etc., and a resistor value. 100 ohms marked, it's 100K in reality. Alright, I've had some success here. After replacing the front end transistor, it still didn't work, but I was getting a signal through it, which wasn't happening before. And then I found that the front end logic ICs had some corrosion on the pins, and I needed to rock them in and out of their sockets a bit, and then everything came alive. I run it through its range of frequencies from lowest to highest, and everything is working perfectly. I probably need to do a quick test of the sensitivity for best results, but otherwise I think it's functional. And it isn't making all that noise since I replaced the power supply zener that it was making before. That boosted the logic voltage up. It was a little bit low. It should have been 3.6 volts. It was more like 3.2 volts. And the controlling zener had apparently drifted with age, although it looked like it was replaced by somebody at some point, maybe not with the right component. So I've got not the one Heathkit recommended, but a similar zener of the same voltage. Alright, this voltage regulator gets not quite impossible to hold your fingers on it, but you'd feel like you'd get burned if you held it on for very long. But it doesn't get any hotter than that, so I guess the heatsink is doing its job. I'm kind of thinking about putting a better heatsink on there, if I have one. Alright, let's take a look at the inside here. Just give a tour. I may have already touched on this in an earlier part of the video. It's all very disjointed the way I'm shooting this one over a considerable period of time. So let's start with the power supply. We have power transformer, very simple plug here for the power cord, and the ground lead goes directly to the chassis. The neutral lead goes directly to the transformer. The hot lead goes through the power fuse and then to the power switch and then back to the transformer. Couldn't be much simpler. There are two secondaries on the transformer. The two red leads and then the center tapped secondary with the blue and the blue-yellow striped leads all going to the circuit board here. So there are actually three voltages that have to be developed here. Two of them are developed off of the supply that only has the the simple secondary winding. These two diodes here, one of them is a zener, the other one's a rectifier diode. So the relatively high voltage, you know, it's up towards 200 volts. Haven't measured it, but it gets halfway rectified by this diode, and then that is applied directly to this capacitor here, 350 volt electrolytic, only 10 microfarads, and that's the slightly filtered supply for all the Nixie tubes. It gives somewhere in the ballpark of 170 volts average, and then through this dropping resistor, this Zener diode, and this capacitor, it gets knocked down to 36 volts, which is for the analog circuitry in the front end of the frequency counter. So that's how we get two supplies off of that simple bit of circuitry. Then the main power supply has got this secondary with a center tap, and it's a full wave rectified but not a bridge. It's full wave because it has the center tap. So these two diodes do that. And then in conjunction with these two transistors here and this Zener diode here, some resistors, this transistor down here, and this transistor. It's not a voltage regulator IC, it's just a power transistor. That develops a 3.6 volt regulated supply, and that's used by all the logic. Now, why is it 3.6 volts? Anyone who's seen my earlier video on the IM-102, which was Heathkit's first digital multimeter, and that came out 2 years after this IB-101, and the IM-102 was actually a circuit clone of a Weston digital multimeter, the 1240, if I recall the number correctly, and that used RTL logic. I'm sorry, that used RTL logic throughout, and so does this. So it's interesting to me that Heathkit in 1970, when this IB-101 came out, was using almost exactly the same ICs, RTL logic, that 2 years later the IB-102 or the IM-102 used almost the same exact series and types of ICs, also RTL of course, that Weston was using in their 1240, and thereby migrated down to the IM-102. So I'm guessing that's still because both companies were owned by the same parent company, and there may have been some cross-pollination between engineers. That's my best guess. It just seemed kind of odd. I would have assumed that the IM-102 would have got its RTL heritage from the Weston meter, and then Heath engineers would have just continued using those same parts, developing the IB-101, but the 101 came out 2 years before the IM-102. So there. Anyway, so it's all RTL logic. That's resistor transistor logic. It's a very simple and robust method of getting logic on an IC, and it was really the first mainstream method of doing digital logic on ICs. And that was indeed the same kind of logic that was used in, for example, the Apollo spacecraft computers and so on. It's very robust, like I said. It's power hungry. All the parts tend to run kind of hot. And it has other limitations, but at least it's robust. Anyway, so these electrolytics here are also part of that 3.6 volt power supply, and the RTL uses 3.6. So down here in this part of the board, the very first thing that the input signal, which comes in right down here where I'm pointing, this is a dual gate MOSFET. It's a 4-lead device, so it has the usual source and drain, but it has two gates, gate 1 and gate 2. And in this particular circuit, I think they're really only using the one gate. The other one I think is just tied down to keep it out of the way. I'll talk about that more in the circuit theory part. I haven't done the complete study yet, so I'm hedging my bets at this point. It has internal Zener diodes. It has the very high input impedance you'd expect from an FET. so it doesn't load a circuit that's being tested. And it has a very wide voltage range that it can handle, and the internal Zehners provide clamping and protection for the device, so you can handle a pretty wide range of input voltages almost straight into that part. There's in fact a dropping resistor that drops anything that remains after clamping takes place within the MOSFET. But anyway, that's the front end that the signal has to go through. And then all this other stuff here, inductors, capacitors, resistors, not really much in the way of transistors, provides a Schmidt trigger functionality to shape the waveform so that it comes out in a level and wave shape that's suitable for the digital logic that follows. The input sensitivity is there. I was not able to get it adjusted per the Heathkit instructions because the internal signal generator that would normally be used for setting the input sensitivity is not working. There's a fault in this potentiometer. It's shorting the signal internally to ground. It doesn't hurt anything around it. It just doesn't provide a test signal at the test point. And it's kind of hard to replace pots like this, and I don't really need it. I just figured out what voltage it would be producing and set up my signal generator or my function generator to provide a similar signal, and then adjusted the sensitivity according to that. Alright, so continuing on. So we got the front end circuit. The crystal is here. That's the internal clock, running at 1 megahertz, which is very typical for frequency counters. And then there are 6, that's 1, 2, 3, 4, 5, 6 decade counters, again all RTL logic, and that divides the signal down to 1 hertz ultimately, from 1 megahertz to 1 hertz. Then also tapped off of there is a 1 kilohertz signal and a 10 hertz signal, and all of those come off the bottom of the board over here, these 3 wires, and go down to the range switch, which selects the appropriate 2 of them. 2 of them are always used of the 3 frequencies available. 1 is used for the gate and 1 is used for another function. This IC has, it's a dual flip-flop, and one of the flip-flops is used to convert the 1 hertz signal coming out of here into a 0.5 hertz signal, and half of that, in other words, when that signal is high, that's the gate for the frequency counter. In other words, controlling all of this stuff. So if you take the 1 hertz signal coming out of all of the decade counters here, and you look at only half that waveform, in other words, when that waveform is high, the period of that, so 1 hertz, take the reciprocal, of course, is 1, take half of that, and that's half a second. Well, you need the gate to be on for 1 second, so you need to slow the clock down, and that's what the 1 flip-flop in this IC does. Turns it to 0.5 hertz, and 0.5 hertz, of course, if you take the reciprocal of it, that's 2 seconds, but that's the full waveform, low and high. If you just look at half of it, the point where it's high, then that's 1 second long. So that's how we get the gate signal. Over here, this IC is a hex inverter, and that means there are 6 inverters in that IC. A couple of them are used, actually 3 of them are used in the gate circuit, and that allows the input signal coming from the front end to be gated into the counter logic over here during that 1 second period. Or when we're in kilohertz, then it's dividing down a 1 kilohertz signal and then dividing that by half to get the proper period for the gate, just like it did for the lower frequency range. This IC down here is a quad NAND gate, and two of those NAND gates are used as part of the crystal oscillator circuit. The other two are used as part of the front end decade counter circuit that's up here. So we've gated our conditioned input signal, and now that has to be applied to a bunch of decade counters. But the frequency is too high for the decade counters that are used predominantly in here. In other words, these 4 decade counters. So some other parts of the flip-flop, and these two are flip-flops, and a couple of NAND gates from over here are all used to form a sort of discrete decade counter, but its frequency capability is much higher, so it needs to be for the highest frequency coming in. That divides the gated input by 10 while also producing BCD output that can be used for the display. And then the output of it is 10 times less, or 1/10 of the input signal, and that makes it now suitable for the remaining decade counters that are all just chained in series. And so the result of this is the BCD data for the units digit, and then the BCD data for the tens, hundreds, thousandths, and 10,000ths positions. These ICs here, 5 of them, are the buffers or latches, or memory if you will, that after a count is taken and the gate is turned off, then that data has to be stored somewhere so another count can be taken on the next gate. So these ICs copy the data from these counters into them and then hold them for the purposes of display. And then finally these 5 ICs take the stored BCD data from these ICs, convert it to 1 of 10 for the Nixie tubes, and also interface to the higher voltage that the Nixie tubes are using. And then finally, if the final decade counter overflows, in other words, if you put in an input that's too high, then it will overflow, and that goes into this IC. This is also a dual flip-flop IC, similar to the one that was used over here. And one of them acts as a single bit counter, just like these are decade counters, and you need only one more bit to handle the overflow, so that's half of this IC. And then that data gets latched into the other flip-flop, just like these ICs latched in the data from the decade counters. So really, this IC is doing what 2 of these ICs did, but only for 1 bit instead of for 4 bits. And then finally, this transistor over here is the device that allows the overrange neon bulb to turn on. So it's interfacing between the logic supply and the much higher 170 volts available for the Nixie tubes and the neon bulb. Finally, there are 2 more neon bulbs here, and those are for the hertz and kilohertz ranges, and they're just wired directly back to another gang on the range switch. So there's no logic involved in the ICs, it's just coming directly off the switch. I think I've covered everything that's in here. Oh yes, just to say a little bit more. Obviously some of these neons have failed at some point. A previous owner has this, it's the original neon bulb stuck in here. It's a kind that's designed to be providing its light out its tail end instead of the nipple end, so it's stuck in backwards here to provide good light in this little round chamber. But interestingly enough, the Heathkit instruction manual gives a part number for these, and it's not the part number for one of these, at least not by today's standards. If you use that part number now, you'd get one of these. It's really the same thing, but it's in a bayonet housing. So internally it's the same thing as one of these, but it's in the bayonet housing. And these plastic shrouds are sized to allow those to fit in there. So I think the Heath engineers were anticipating that somebody might use the one that's inside of a encapsulation or a housing and allows those to fit in. But they don't actually go in bayonet wise. There's no actual socket, so they just get jammed in there, and somebody's obviously put a little glob of hot melt glue on there to hold it in place, and they've used different wires, not the original wires that would have come out of a discrete bulb. And the same thing was done over here. I considered replacing those, but I can't find these originals, and these really are the same thing, just in a more industrialized housing, so they work just the same, and I'm not going to mess with them. Alright, for a little demonstration, I don't have this put back together yet completely, but I've got the top case half on just to shield it from my work light. I've got a BNC cable going up to my signal generator, and it's currently set for 1 hertz at 1 volt sine wave. I've got the kilohertz hertz switch set to hertz, and I should mention, if I didn't already, that this is a 15 megahertz maximum frequency counter, so pretty low frequency. I'll turn it on, give it a moment for the gate, and it's zeroed out. It's indicating hertz. I'll turn the signal generator on. Alright, we had to wait a moment for a couple of gate cycles to go through so everything would propagate through the circuit. It's indicating 1.0 hertz. With only 5 digits of resolution, we can't be having fractional values here, but since it's hertz, you know, it's a really low frequency to start with. Let's go up to 15 hertz, right on the money. Let's go to 274 hertz. It always is asynchronous with the input signal, so if I happen to change the frequency right in the middle of a count cycle here, you'll get 1 second's worth of inaccurate data before it takes another count and gives you the correct number. Let's put in 751 hertz. One inaccurate, 751. Let's put in 9.5 kilohertz. Pretty darn close, there we are. 9,500 hertz. 12555 hertz. 12555, right on the money. And if I go up to 90 kilohertz, it bonks. Looks like I have a somewhat defective Nixie tube there on the 8. Doesn't want to give me an 8. I hadn't noticed that before. Yeah, it'll show me a 9, but the 8 is a defective one. Maybe I'll see if I can find a replacement Nixie for that. Anyway, so it's right on the hairy edge of overranging. I'll give it an overrange, and it gives me the overrange indication. So I'll switch up to kilohertz. It has a faster gate now. So that should be 110 kilohertz, and that's exactly what it's giving me. 180 kilohertz. Very fast update now with the very short gate time. 320. Let's go right up to 10 megahertz. 10 megahertz, boom. It's right on the edge, so it's trying to flip to all nines, or 0999, but it's right there. Let's go up to 12 megahertz. And it's kind of bonking here. It doesn't like the higher frequency. It's supposed to go to 15 kilohertz, or 15 megahertz. So that was just the sensitivity being a little off. I just tweaked it slightly, and now it's giving me the 12 megahertz. It's right on the point of rolling over, so that's why it flickers. Let's go to 13. Got that. 14. And once again, it doesn't like me. Maybe I have to tweak it some more. Yep, got it there. And let's go up to 15. And that's, according to specifications, the highest it should be able to do. What if I go to 16? Yeah, it bonked. It's right on the edge of getting it through the front end. I think the amplitude keeps dropping until it no longer satisfies the digital logic. Anyway, okay, it's 12.345 megahertz, or 12,345 kilohertz. Alright, there's the beauty shot. Alright, let's take a look through the Heathkit manual. This isn't an original, but it's a faithful copy produced by manualman.com. IB-101. Has the overview page, picture of the unit, frequency counter, model IB-101, table of contents. The model IB-101 Heathkit frequency counter is a compact, lightweight, and rugged digital frequency counter. The basic functions and uses of this instrument are like those found in other high-quality frequency counters. Many features make the counter convenient and easy to operate. 5 cold cathode display tubes, that's Nixie tubes, an overrange lamp, and 2 range indicator lamps provide an easy-to-read readout. The readout accuracy is assured by the modern digital techniques and a crystal-controlled clock. The high-impedance MOSFET input circuit presents minimum loading to the circuit under test, and the automatic level triggering feature provides simple hands-off operation. The counter's 2 regulated power supplies can operate from either a 105 to 125 or a 210 to 250 volt 50-60 Hertz AC power source. Lightweight and reliable plug-in integrated circuits minimize and simplify maintenance. The detachable test cable and line cord and the 3 detent position bail-like handle make the counter completely portable. The unique bail handle can be used to position the counter at a desirable viewing angle. And then we have the parts list, spanning 3 pages, and on a fold-out are parts identification drawings. Then we get into the step-by-step guide, starting with about half of the circuit board, putting in resistors, and then the other half of the board putting in resistors, then mounting the IC sockets for about half the board, continuing with that, installing ICs in the sockets, mounting capacitors and large resistors, mounting diodes, mounting trim potentiometers, inductors, crystal, and a test point pin, and mounting transistors, mounting other odds and ends such as the dual gate MOSFET, some of the wiring, and the power transistor, installing some additional wiring that'll go to the front panel and elsewhere, assembling the chassis, mounting the switches and fuse holder, mounting the transformer and AC power cord socket, wiring the transformer primary for one voltage or another, mounting the front panel and bezel and the BNC input jack, mounting the lamp holders, installing the bulbs in the lamp holders, installing the Nixie tubes in their sockets. Some more assembly diagrams, wiring up the AC input circuit, wiring up the range switch, making a light shield, or not making it, but folding it up from some furnished cardboard. Then the cabinet shell assembly. Making the test cable that comes with it, in pieces of course. Doing initial checkout. Final assembly. Mounting the handle. Putting the mounting feet on. Calibration without instruments. Adjusting input sensitivity. Calibration with instruments. A block diagram of the counter. Several more diagrams having to do with calibration and testing. Operation spanning about a page and a third. And in case of difficulty section, troubleshooting chart, factory repair service, specifications, 1 Hertz to 15 megahertz minimum. It can go higher potentially. Accuracy is plus or minus 1 count, plus or minus the time base stability. Gate times are either 1 millisecond or 1 second with automatic reset. Sensitivity from 1 Hertz to 1 megahertz is less than 100 millivolts RMS. 1 megahertz to 15 megahertz, less than 250 millivolts RMS. Trigger level automatic. Impedance is 1 mega ohm shunted by less than 20 picofarads. Maximum input is AC only, 200 volts RMS, 1 Hertz to 1 kilohertz. D rate 48 volts per frequency decade. And there's a chart illustrating that. Frequency of the time base is 1 megahertz crystal controlled. All the other stuff we already knew. The circuit description spanning 4, 6, 6 pages. Some chassis photographs. Circuit board X-ray view, and in this case they really made a hash job of it. This is a photocopy of the original, but the original they worked from had the top and bottom foil images, which would be different colors originally, and here it reproduces different shades of gray. They're badly misaligned. You have to really scratch your head sometimes to figure out what goes with what. Replacement parts price list. Identification chart for the Nixie tubes, transistors, diodes, and the various ICs, all of which are digital. There aren't any analog ICs in this particular product. And then the schematic diagram as a fold-out. Alright, let's look at the schematic diagram and go through the circuit theory. We'll start out with the power supply. We have our AC line cord, and the ribbed lead, which should be neutral, is connected to one side of the power transformer primary winding. The smooth lead, which should be AC hot, goes through the power supply fuse, then through the power switch to the other side of the primary winding. And if you've got it, this is as shown for wired for 220 volts. This is the way the winding is set up for 120 volts, but it essentially works the same way. We have the two secondaries, as I already mentioned. The high voltage secondary, I've measured the winding at 160 volts RMS. Nice sine wave, one side's reference to circuit ground. We have a half-wave rectifier with a very small filter capacitor, but the loading on this circuit is very low, and this provides fairly adequate filtering. And that is our 170 volt source for the high voltage Nixie tubes and the one neon, or the three neon lamps actually. Now, again, the filtering on here is adequate for this purpose, but it's not good enough for other circuitry. So we go through this 5 watt 10K resistor, which drops most of the voltage, and then we have a 36 volt Zener diode, which has 36 volts across it. Again, the rest of that voltage is dropped here. That's 170 volts minus 36 volts. And therefore it's a fair amount of power being dissipated, and that's why it's a 5 watt part. Sits there and gets smoking hot on the circuit board. And then there's another capacitor, in this case 100 microfarads, across it to filter that, and you get a fairly smooth 36 volts, which again is used for the analog front end. I'm not actually sure there's anything on this circuit that uses that besides the front end FET. Then we go to the power supply for all the logic, which is the bulk of it and consuming the most current. So we have a full wave rectifier here. It's not a bridge, it's just two diodes forming a full wave rectifier, and that's possible because the secondary center tap is grounded and we're taking off the two sides. So we always have one half of the waveform, the other half of the waveform being mixed together here. There is a 2000 microfarad capacitor, so pretty good smoothing. Ends up being about 5.8 volts DC. And the first thing we do is have a Zener diode reference of 4.7 volts. And normally you would just have a resistor like this, resistor for this Zener, but in this case it's a more sophisticated circuit. It's a constant, or not a constant current supply maybe, but a current limited supply to the Zener. This is the primary path here. That raw voltage comes here, goes through a low value 21.62 ohms, then through this power transistor, and then through the Zener to ground. And so there's not a lot of throttling back. This transistor is presumed to be on initially, fully on or nearly fully on, and that's assured because it's an NPN or a PNP type, and the gate is pulled low through this resistor, thereby assuring plenty of gate or emitter to base current. So it's turned on. Now, if you start pulling enough current through here that the voltage drop across this low value resistor starts increasing, and that resistor is placed across the emitter base junction of this smaller transistor, and so when that voltage gets high enough, then it turns this transistor on and it starts dumping more current down here, which raises the voltage drop here. Therefore, this point is at a higher voltage than it was previously. It's closer to the voltage here. Therefore, this transistor starts turning off. Being a PNP, that's the way it reacts. And when it just starts turning off, then its internal resistance from emitter to collector gets higher, and it acts as if you just had a resistor here that gets higher when the current gets higher and is lower when the current is lower. So it's an active voltage dropping mechanism for the Zener diode. So we have 4.7 volts here, and we have a Darlington transistor, a small transistor driving a bigger power transistor. And these being silicon type transistors, they have roughly a 0.06 volt drop from base to emitter. So we take the 4.7 volts here, subtract 0.6 volts for this junction, 0.6 volts again for this junction, and you end up with exactly 3.5 volts, which is what the voltage out here is. And there's another large capacitor filtering that. So that's how the 3.5 volt source, which powers all the logic ICs, is derived. So just a quick recap on how frequency counters work in general. You have some sort of an internal clock that's usually a fairly high frequency, and 1 megahertz is pretty common. And you divide that down a bunch of times to get much lower frequencies, but because they started with an accurate higher frequency, by the time you divide them down by several orders of magnitude, they're actually very stable and not likely to change hardly at all. Any small error up in the 1 megahertz end is divided down by 6 orders of magnitude, therefore virtually no error down here. This circuit provides, at this junction, each of these is a decade counter, I should say. So we end up with a gate signal produced by this. That divided down signal, say 1 hertz, after it's conditioned by more logic up here, it becomes a 1 second pulse that's used as the gate. Now if you tap off in the middle of the divider string, it's 1 kilohertz instead of 1 hertz, and that provides, by the time you go through the processing up here, it provides a shorter interval, 1 millisecond, as the gate. So you either have a 1 second gate or a 1 millisecond gate. And that gate is used to admit signals coming from the input and passing them on to the main counter chain, which is over here. So whenever the gate is open, the counters go brrrr, and they're counting up really fast in that 1 second or in that 1 millisecond, and then when the gate closes, they stop counting because the input signal can't get through to them. Right after the gate closes, then the same logic that created the gate signal now provides a transfer signal, which tells all that data that's in the counters to be transferred into essentially memory devices. And immediately after that, then there's a reset signal that's generated, and all the counters get reset, and shortly after that there's another gate signal so it can count up again. In the time when all the resetting and transferring is, or the time when the counting and the resetting is going on, these memory chips are holding the most recent count value, irrespective of what the counter is actually doing at the moment. And then those stored values are presented to the decoder drivers, which convert the BCD digital values from each stage of the counter and present that to the output devices, in this case a bunch of Nixie tubes. So now let's look at that in more detail. The clock signal here is a classic 2-inverter oscillator. In this case, the inverters are formed from 2 NAND gates with one side tied low to ground. They operate as inverters. And there's some capacitors and the crystal and some resistors for stability. One of the capacitors is adjustable, so you can force the crystal to oscillate at something very slightly higher or lower than its nominal value of 1 megahertz. And that's the way you can trim it for best accuracy. you end up with this 1 megahertz signal. It gets divided down to 100 kilohertz, divided down by 10 again to 10 kilohertz, divided by 10 again to 1 kilohertz, as it says here, divided by 10 again to 100 hertz, by 10 again to 10 hertz, by 10 again to 1 hertz. And depending if we're in the hertz or kilohertz range, the switch picks off the 1 kilohertz signal or the 1 hertz signal and passes it on to this inverter, which just flips the signal upside down, and then it presents it to this flip-flop. And the flip-flop is just set up to toggle its outputs every time it gets a pulse here. So for 1 second you've got a pulse and the flip-flop goes one way, and you could say that's the gate side of things, and then the next pulse it flips the flip-flop the other way, and now the gate's gone, and now it's time to do a transfer and a reset. The actual gate signal is tapped off of this output of the flip-flop, and it goes up to this flip-flop, which is the first of 4 flip-flops that are combined together to form a decade counter with BCD outputs. And the first stage is almost always done this way because the particular ICs that are used are faster than if you had them integrated into a single flip-flop IC. It's not true with all logic families and all versions, but especially in these earlier products, it seems that these particular IC flip-flops were faster than the decade counter ICs that were used downstream. To make a proper decade counter out of these flip-flops, we also need to have a couple of inversions or an AND function with an inversion, and that's what these other 2 NAND gates, remember that we used the other 2, there are 4 NAND gates in that one particular IC, so 2 of them are used here, 2 of them are used here, but one's acting as an inverter, so it's really just making it an AND gate. And that, combined with these, forms the first decade counter. Now how do we get into the decade counter? So we've got our input comes in here, it goes through a 100K resistor and then through a 1 meg resistor to ground. That establishes the input impedance at somewhere a bit north of 1 mega ohm, which is pretty typical value. This resistor is bypassed with a small value, 100 picofarad capacitor, and its capacitive reactance goes down as the frequency goes up. So because some of these other components perform less efficiently at higher frequencies, they need a bit more voltage to operate properly, and therefore this is a bit of an attenuation that is formed here. And because this resistor acts like a smaller resistor when its parallel capacitor's capacitive reactance changes, then you essentially have the voltage divider is skewed to have more voltage at its output than it would at lower frequencies. So this is just a frequency compensation thing so that the meter works properly throughout its designed frequency range. So we come through here and we go into this dual gate MOSFET. Well, if you ignore all the diodes there, it just looks like this. So normal N-channel depletion mode MOSFET with not 1 gate but 2 gates. And you could use them, you could tie them together and it just acts like 2 MOSFETs with a single gate wired in series. Or you can tie one of them off to a fixed voltage and just use the other one, or you can use them both. You can make a mixer, for example. When it's used in the manner we've got here with 1 gate tied to a fixed voltage, in this case it's just through a resistor capacitor network to ground, so it's held at a fixed voltage, then it's as if you had 2 MOSFETs in series, with one of them having its gate held at a fixed voltage and the other one having a signal on it. And when you do that, it's what's known as a cascode, almost like cascade, but with an O instead of an A. And that's a scheme that's used to eliminate or reduce the Miller effect that occurs as a parasitic in lots of semiconductor transistors that causes them to behave poorly at higher frequencies. By using the cascode scheme, it makes the circuit essentially immune to the Miller effect. So what they're doing here is they're basically just using an FET to condition the input signal to provide a very high input impedance on the input end and a low impedance on the output end, so we don't load down whatever circuit we're testing, and also provide a bit of amplification in the bargain, and doing it in a cascode configuration so the parasitic capacitances don't mess up the way it works at higher frequencies. Now, there's also protection circuit in here. This particular dual gate MOSFET has internal Zener diodes. They're shown as regular diodes here. A bit of a drafting error. They're actually back-to-back or face-to-face Zener diodes, and those provide input clipping in such a way that fairly high voltages applied here don't damage the device, and are also squared up somewhat by that clipping action. So it looks more like a digital signal than an analog signal, if indeed it is an analog signal. So amplification, impedance matching, frequency compensation, and input attenuation, clipping, and conditioning, all in one little 4-terminal device. Okay, now we have to provide a Schmitt trigger. Almost every frequency counter front end, if not every frequency counter front end, has a Schmitt trigger, because you may not be measuring nice square digital signals. You may be measuring sine waves or waveforms with all sorts of crazy shapes to them, and you need to clean it up and make a nice square wave type of waveform out of it with nice sharp rise and fall times. And this whole thing here is part of the Schmitt trigger. The actual Schmitt trigger is just formed from the classic topology of a non-inverting buffer with positive feedback. You've got two inverters, one after the other, so it's non-inverting, and then you have feedback that, so when this is high, this is low, and this is high, so high to high makes it non-inverting, and also positive feedback. So that's the classic form of a Schmitt trigger. And what a Schmitt trigger is it's a device to use waveforms that don't change cleanly, like gradually changing analog waveforms or digital waveforms with sloppy rise and fall times. It has a different threshold for rising signals than it does for falling signals. So it doesn't chatter. That's another thing. If you have a threshold on this IC, let's just say it's half the power supply, which is 3.5 volts here. Let's just say it's 1.8 volts or something. The threshold, without the hysteresis provided by the Schmitt trigger, if you had an input signal that was loitering around the threshold voltage, a slowly changing signal. When I say slowly, I mean slowly in the world of high-speed digital logic. To us, it would still seem like a fast-changing signal. Because if that signal is loitering around the threshold voltage, it could one moment see it as a high, one moment see it as a low, and the output could chatter. And while it's really just one slow change over here, it might be reflected or converted into multiple changes, and you get an inaccurate count. So by putting in the different thresholds in the Schmitt trigger, it forces it to reflect the actual frequency of the input signal while it's being converted into a digital signal. Now this one's enhanced a little bit by the presence of a small inductor here, 600 whatever microhenries, and that just fine-tunes its response. Now, sensitivity is the other thing. We want to make sure that this isn't overly sensitive, but you want to make sure it's sensitive enough that even fairly small signals that you might be measuring will be registered by the frequency counter. So let's look at that. We have a voltage divider starting with the 36 volt power supply. Voltage divider is 1 resistor, 2 resistors, 3 resistors, ignore the inductor for the moment, and then this resistor. So a voltage divider made of 4 resistors, and the output is taken off from the middle of those 4. You adjust the bottommost resistor to fine-tune the signal. If you've got no input signal, it's just sitting there unconnected, and whatever voltage is here, you want to adjust it so it's just below the input threshold of the first Schmidt trigger gate. Almost triggering it, but not quite. So that's why this is adjusted. And then if you get a small signal coming through here, after whatever amplification it may get here, it's just enough to trigger the threshold, or the IC past its threshold, so it starts passing the signal through. But if you don't want it to be too sensitive, because then it's more responsive to noise. So there's a protocol for adjusting it for the optimum sensitivity, and that's what that trim pot is for. It just skews the voltage divider around. Now, a couple other things I can say about this, because again, the circuits tend to respond a little worse at higher frequencies. You need to boost the voltages a little bit at higher frequencies for it to work the same as it did at lower frequencies. That's what this capacitor here is for. As the frequencies get higher, the capacitive reactance gets lower. It shunts out this particular resistor in the overall voltage divider, making a greater amount of resistance here, and therefore a greater voltage drop, and therefore a somewhat higher voltage. So it's a way to boost the signal slightly at higher frequencies for best overall response. And this inductor here does something similar for the lower part of the voltage divider. Its inductive reactance changes in a way that has the same general effect. We're both trying to boost the gain slightly on higher frequencies. Alright, as I already said, we have the first decade counter is comprised of individual flip-flops with help from an AND function. The output is A, B, C, D as I penciled in, going into a buffer storage or a memory device or a 4-bit latch. That's the terminology I prefer to use, a 4-bit latch. And then the output of that is fed into the clock input of the first actual decade counter. Its ABCD outputs, BCD in other words, is applied to the next latch. Its overflow goes to the next decade counter, which has its own latch, and so on until we get to the end. And then when its output turns on, indicating an overflow of the whole counter string, then this transistor inverts it, applies it to a flip-flop where it's locked in. It's registered, if you will, that an overflow has occurred. So in that case, you might say you've got a value in this decade counter, a value for the tens, this is units, a value for tens, hundreds, thousands, and 10,000ths. And if there's an overflow to the 100,000ths, it's picked up by this single bit held by this flip-flop. So we have the gate has been allowing signals to get in from the input to the counter change. It's been counting up to whatever value it can count up to before the gate closes. And again, that's the signal coming from down here. It closes the gate here, and therefore the signals cannot get through to the first decade counter, and everything just stops counting. Immediately after the gate closes, the other output of this flip-flop turns on, and it has to be conditioned because of the way the flip-flop is working. You don't want to perform the next step of the function erroneously, so you actually need to combine this signal with this signal. and you'd usually use an AND gate for that. Well, they didn't have an AND gate left over from anything else on here, so what they did is something slightly clever. They used a wired AND function. These being RTL logic devices, this is what they actually, this is the exact schematic. It's the VCC, or the positive logic power supply, through a resistor to the collector of a single transistor. The emitter is tied to circuit ground. The input goes through a certain value resistor to the base of the transistor, and therefore when this is on, the transistor is on, which pulls down against this pull-up, and their output is off. So, and 1 on the input is a 0 on the output, and vice versa. So that's why it's an inverter. So this is essentially, if you ignore the pull-up resistor, this is like an open collector transistor, which means you can combine them in parallel. And that's exactly what's happening when you have 2 of these in the form of 2 inverters in that IC with their outputs shorted together. It's really just like this. So 2 particular inverters in the same IC with their outputs shorted together, and it provides a truth table which looks more like a NOR function, but a lot of the logic in here is working with negative logic, and there's also another intrinsic inversion in here that's too complicated for me to talk about here. Suffice to say that in the world that this logic is working, the function performed by these 2 inverters wired as an AND actually does function as an AND, even though the truth table makes it look more like a NOR. So it's a wired logic function to make up for something they didn't have on one of the other ICs, and they had a couple inverters left over. This feeds down to here. This is another gang of the range switch. And by the way, this is only necessary when you're in the slower range, the Hertz range. In the higher frequency range, this isn't, what this is doing isn't so important. So we just use the 10 Hertz signal from this counter if you're in the kilohertz range, and you use this conditioned 1 Hertz signal if you're in the Hertz range. And the end result both gets differentiated by these 2 components, this capacitor and resistor, to reset or clear this flip-flop. But more importantly, it goes through another differentiator here. And by differentiator, I'm just talking about, let's say you have a signal that maybe goes like this on the input, and you might turn that through a differentiator into a signal that looks like this, or something of that sort. So it's turning it into a very short pulse. And that's what this is doing. It's turning the anti-gate signal into a very short pulse, which gets inverted, and then that's called the transfer command. And it feeds to all of these latches and tells them to take whatever's in the counter and lock it into the latches, so we have a snapshot of it. And by the way, we have to have a latch for this overflow, and that's what the other half of this dual flip-flop is doing. This is the latch. So this is the equivalent of this, and this is the equivalent of that, but only for 1 bit. So that transfer function does all of that. And now once everything is stored, there's one more differentiator here, and that's provided by these 2 components, this capacitor and resistor, and its performance tweaked slightly by this diode, and then that's presented after an additional short time delay caused by these 2 components. It just shifts it over a little bit, delays it slightly, and that's to avoid a logic race between other signals. And then that operates this transistor, which generates the reset pulse. And it hasn't, because it's driven by the transistor, it's got enough oomph to drive a whole bunch of outputs, including the clear on all 4 of these flip-flops, and the clear on all of these counter ICs, and to reset the latch over here as well, or on the flip-flops here for the overflow. So the sequence is open the gate, take a count, close the gate, do a transfer to move or make a snapshot of what's in the counters to the memory or latches. Then, after the data has been latched and saved, then issue a reset to reset the counters back to 0, and then open the gate again to take another count and repeat, repeat, repeat. Now, I already covered this pretty well, but so now we've got a bunch of stored values in these latches, including the overflow values stored in this flip-flop, and those all have to be converted to drive the appropriate indicator. So we have these specialty ICs. They're decoder drivers intended for Nixie tubes, so the outputs are not logic level. They're intended to be open collector outputs that are designed to be able to withstand the higher voltages that are present when you're driving Nixie tubes. In addition to that, it converts the BCD code for each step, the units, the tens, the hundreds, and so on, converts those BCD codes into a 1 of 10. So if you've got a BCD code of 000, then it turns on the 0 output. If you've got 001, it turns on the 1 output. If you have 010, it turns on the 2 output, and so on. I only counted out 3 digits when I said that. It should have been 4 digits, but never mind. It's still BCD. And then whichever anode to cathode path has a path to ground through the decoder driver, current will flow through that particular segment of the Nixie tube and cause it to light up. And there's a current limiting resistor, and there's one for each device. Now, in the case of this, I don't know why they did it this way exactly, because just about every frequency counter that Heathkit made, besides this one, actually does the same thing with the overflow Nixie or overflow neon bulb. In other words, it has a transistor provide a path to ground, and then current goes through the current limiting resistor, through the neon bulb, and through the transistor to ground. But here, they chose to have the bulb normally on all the time. It's always powered, but then have the transistor short the bulb out, thereby turning it off. And then that's driven off of the inverting output of this flip-flop. I think they could have just as easily done it by having the neon bulb over here and providing a path to ground and taking the base off of this output, but for some reason they chose to do it this way. Alright, is there anything I forgot to cover? Oh yes. The unintelligent indication of which frequency range we're in. 2 more neon bulbs, one for the Hertz mode and one for the kilohertz mode. We take the 170 volts, you go through a current limiting resistor, through a third gang of the range switch, and whichever position it's in provides a current path from the high voltage through the current limiter through one or the other of the neon bulbs to circuit ground. Therefore, that one that's selected will light up, and the operator who's looking at the display instead of at the switch can easily tell which mode or which range he's in, so he can interpret the results. And that's the whole circuit, folks. Alright, the IB-101 is supposed to have a light shield. They were always usually made out of cardboard, although I did find some Heathkits that used a plastic or a sheet metal light shield. And the light shield is there with the Nixie tubes in particular because they're basically transparent except for the internal electrodes, and ambient light that comes out of the room goes through the front window of the frequency counter, can pass between and through the Nixie tubes, illuminate things on the inside of the meter, on the circuit board and so on, reflect back, go through the Nixie tubes or between them and out the front window again. And you see all that stuff, and it makes the display look crappy. It's better when the cover is on completely, but you still see more artifacts that you don't want to see when you just want to see the Nixie tubes. So the light shield goes behind them and prevents that ambient light going into the counter, reflecting and coming back out. Because of congestion on the circuit board really close to where the Nixie tubes are, this is only going to be a 3-sided object. Ones I've made before often have wings on them or something. So you can picture this is like a bracket with a top, a side, and a flange on the bottom. The Nixie tubes go under this. The front window of the counter is right here. Then the Nixie tubes and their sockets, and then the actual light shield is this part primarily. This part is there to help keep the Nixie tubes straight instead of leaning or tilting. It keeps them aligned, and it also provides a top for the light shield. And because the front edge sits on the inside surface of the front window, that provides stability so this doesn't want to tip forward or something. And then the bottom of it has a little foot or flange that sits right down on the circuit board, and that could be stuck down with a little bit of adhesive, or it can just stay there. I have it sized so it goes right up against the fronts of the IC sockets. Now normally I would have a wing or something on the side here, but there's objects on the circuit board that come right up to the Nixie tubes, so this would get in the way, and if I put a big cutout in it, then it pretty much defeats the purpose of having it. And there's other obstructions and things that get in the way, so it really has to be supported from this flange and from the front end touching the window, and also a little support from the Nixie tubes themselves. I've taken measurements in millimeters. It seems to work out nicely in millimeters. And I kind of like it that way better, because if I set up Tinkercad in millimeters, then everything is real easy with the math and the dimensioning. I've decided to make this out of 3 panels that are just abutted. So I'm going to have a seam here and a seam here, and I've worked out the dimensions of each of those 3 plates. And this one's going to be more complicated because it has the 5 circular holes in it. Alright, I'm in my Tinkercad web page here. Go to my designs, and I have a whole bunch of the dust cover bell plugs for the Martin's horns that I did a video on recently. And then I've got a light shield for the IB-101, a light shield for the IM-103. I think that's a typo. I think that should have been 102. So I'm going to create something new. 3D design. And it's going to give me the workspace. And I've got to go at it. So I just dragged a cube over to the workspace, or the work plane, and I need to have an object which lays flat, 1 millimeter thick. I'm verifying that my system is still set up for millimeters, and I've got to change the dimensions to be 20 by 150. So I click here, and I want it to be 150 wide. Boom, it does that. Drag it over here, and For this dimension I want it to be, well, it is 20 already, good. And then I have to go to the vertical dimension and change that to 1. So that looks more like it. And I better put my holes in there while I'm thinking of it. So I'm going to grab one of these and drag it around. And this is going to be a hole with a inner, well, since it's a hole, all I have to do is specify the outer diameter, and that'll be the inner diameter once I put it inside the plate. So I need to go here and put in 4 millimeters by 4 millimeters and set the height to 1 millimeter. End up with this little disc. By nature, in the program, it means it's sitting on the workspace or the work plane. You can see that it's, wait a second, it's, where is it actually? It's hovering. It is not where I wanted it to be. So I have to click up on this thing and make sure that it says it's 0, but it looks like it's hovering. I have to work that out. Okay, I corrected an arithmetic error that had these plates 150 millimeters long when they actually should be 90 millimeters long. That looks a lot better now. I've got my holes positioned along the bottom edge, or the front edge or back edge, whichever you want to think of it, and properly spaced. Now I just have to get them in that direction by 8 millimeters. And the easiest way to do that is to group them, which I can do by dragging a box that touches all of them. And then Control G will group them so they all act as one object. And now when I move them, I'll get a dynamic dimension window. I want to go up by 8 millimeters and sideways by 0. So I've drifted a little bit to the left. I wanted, what I say, 8 millimeters? 8 millimeters and go to the right. A couple notches to get that, or to the left. 0 and 8. There we go. And these are centered on this line here, and that's 10 and 2, so that's 12, and that's what I should have to the front of that plate. So those are properly positioned, and I should have 14 millimeters to the right, and they're centered on this point here. So that's 4 and 10, that's 14. Good, they're in the right position. And now I just drag a window around the whole thing, select them all, and Control G them to make them into one object. And now they show up with the proper holes. And I can go back into my perspective view. So now I can turn around, look at it from different angles and stuff. I'm just going to move it up here and get it out of the way. Now I have to do the vertical plate. And that will be another box dragged onto the work plane. And that's got to be 30 tall. So 30. And it needs to be 90 wide. But it only needs to be 1 deep. Oop. And just so I can tell them apart, I'm going to change the color, make this one green. There, so verifying my dimensions. I've got a 1 by 90 and a vertical of 30. Good. So that's correct. And I'm going to move that out of the way as well. And now I've got to get my foot flange. So I need another box. And right off the bat, I'm going to make this one yellow. And it needs to be 90 wide and 8 and 1 high. Now this one needs to be 2 millimeters. I want the foot to be a little thicker. There. All the pieces are here. So, I'm going to move the foot plate down so it's on a major grid space. And this guy needs to be raised up 2 millimeters. Otherwise, when I try to slide it so it overlaps, the yellow one will just slide over. So I need to go up to this guy and grab the little raise tool here, move it slightly so it gives me a prompt, and I want to raise it by 2. So now I can see it's got a shadow, and I'll be able to move it on top like that, which is what I want. Now the combined height of the flange and the light shield plate is 32 millimeters, so I need to raise this guy up, grab its raise tool, and I want to put 32 millimeters in there. So now it's way up in space here. It has a nice shadow. Just drag it over until it sits on top. Looks like everything is aligned the way I want it to be. I like that it even puts the shadow with the light spots shining through from the top. That's a nice touch. So that's really my light shield. And what I really should do here is I have to rotate the whole thing so it sits on one edge or it'll be unprintable. At least not without extensive supports being printed. So I'm going to select the whole thing and group it into one object. So now it all shows as one color. And I need to rotate it up on one end. So I select the whole object, and if I hover up here I get a rotate tool that gives me that, and I can let's see, I can go around until I've got it (180 degrees). So now it's that way, but that's not what I really wanted to do. Now I have to switch my view around, scroll out a little bit, select it again, and now do a rotate of 180 degrees. There we go. And take a look to see if it's hovered. I don't think it is. I don't see a shadow. And if objects are not on the work plane, then they have a shadow below them. So, but that's really not what I wanted to do. I still haven't oriented it the way I really need to orient it. I've just been flipping it around and doing all sorts of crazy stuff. So what I really need to do here is go to 90 on there, and now it's sitting on its side. Oops, the thing went underground, so I need to raise it up. It's minus 28 right now, so I gotta put in 0 and bring it up to the level of the work plane. That's more like it. And I want to verify that I haven't goofed up my dimensions by rotating things. I don't think I have. Alright, I've verified that it hasn't got screwed up or flipped in the course of doing all that. So now I can just go ahead and export it. I want to export it as an STL file. And I should have named this first. Fantabulous Hilar is what it's called, and I didn't want to call it that. I wanted to call it IB-101 Light Shield. So now I have to export it under the new name. STL file. It's created that file. So now I've dragged the file into my folder for the IB-101 where I'm keeping everything. And I gotta go and send it into the Prusa Slicer. Okay, got my Prusa Slicer software open. I'm going to get my folder that has that file in it. And I'm going to drag it onto the work table. And there it shows up. All looks good. It's in the correct orientation. And now I'm going to slice it. And slicing is completed. It's a very simple object. And I'm going to export the G code. And I can go and look at it on here on the SD card. We'll have to move it to there first. So let's see. Yep. There's the G code there. So I'll drag it over onto my SD card that I use for communicating with the actual printer. It's taking its time, it's thinking. There we go. And now it's there on the SD card, and I can close that out. Very good. Got it on my SD card, and as it always does, it takes the newest file and puts it at the top. It assumes that's what you're probably going to want to print. So I just select that, and it says it's going to take 1 hour and 48 minutes to print it. And I got my little audible timer ready to go as soon as it decides it's going to print it, waiting for the bed and the hot end to warm up. The hot end is already the correct temperature, but the table is a little too hot, so it's cooling down. There we go. Get rid of that crap that's hanging off of it. And it's going to do its calibration. It's going to a while before I can see much. It's getting to it. I've started my audible timer so I can go away and do something else and be alerted when it's done printing. Progress is being made, and it looks like it's already made a couple of holes, or one hole anyway, in the top plate. Well, the piece fell over on the print table. Obviously the grip that small surface area has wasn't sufficient, so I'm going to have to put a little flange on the side of it just so that it has more grip on the table. Alright, I've added this flange down here. I think that'll hopefully give it enough. I'm thinking about adding something on this side too, but I have to double check whether that's going to hit anything on the chassis or circuit board. Nope. That area is not clear. I can't put anything there. So it's going to have to be that. That's the only place that makes sense. And that should improve it dramatically, so hopefully it'll do the trick. Good progress is being made. Only about 27 minutes left to go on printing. It doesn't show any signs of falling over this time. And it's just completing the fourth hole. There's a little bit of fluff floating around there in the exhaust of the cooling fan. Yep. Alright, that came out. There's a little bit of the usual fuzz that gets on there. Tiny little strands of plastic. And there we are. And let's see here. It should be able to slip in like this and then swing the bottom in. That was the intention anyway. There we go.